So the user can decide whether they want each, I would say this would be the period function, each function to write graphically or textually. And now I will start to present the technology. As I mentioned, there are two pillars. First, understanding the idioms that a quantum developer thinks with. And second, to develop or create the technology which will take those idioms or high-level description into low-level code, but not by transpiling to very similar low-level functionalities, but by understanding that what the user needs, what the developer needs, is to be functionally correct, and not to be correct on any bit and piece because they don't care about it. So this is what you need to have in mind when I will describe the technology or the automation. So let's start with examples, and as usual, when we learn by examples, we will start from the simple and gradually grow. So let's look at the most common working horse of quantum computation, which is the multi-controlled gate, in this case multi-controlled X. So this is the function. What the user cares about in this particular case is that this function will be implemented. It has 6 control bits and one target bit in this particular case. It can also be controlled on zeros or ones, it doesn't really matter. And this would be a particular implementation of this function. It actually uses no auxiliary qubits. So the same number of qubits in the physical implementation as in the logical description is what the user wants. It has 168 CNOT gates and the depth of 225 in terms of CNOT gates. I believe it is optimized. You cannot do better, as far as I recall. And this is a different implementation of the same function. This would be a 9-qubit master implementation of the same 7-qubit functional multi-control knot. So here you trade off 2 additional auxiliary qubits if you have them for much less CNOT gates. There could be an 11-qubit master implementation, and so on and so forth. And in this particular case, anyone here coming from engineering, one of my other hats, by the way, I have so many hats because I'm just very older than you guys. When you reach my age, you will have at least as much expertise as me. So if we are looking from an engineering perspective, we just have a trade-off table, which is so common in any engineering EDA tooling. And we see that the machinery, that the automation, that the synthesis engine needs to trade off between the widths of the function in any particular point in the algorithm. I did not tell you where this MCX is functionally located in the algorithm. So at any particular point, the synthesis engine needs to trade off between widths, number of available qubits, memory if you like. Actually, the auxiliary qubits, it would be just the same. The number of CNOT gates, depending if the gates are noisy, depending if it is 2-dimensional connectivity, so any CNOT gate would require many swaps or not. So the number of CNOT gates, the qubit depths, and this for any function. We can go on to many more to functions which are larger. You see the point here. So this was one example. Let's look at another